let's say here's the temperature, or I'm sorry, um, here's the temperature, and then maybe this is, I'm going to add heat to it, here. So let's say I have my ice cube here at no, yeah, this will be Q and this will be T, yeah. I want this one to be minus 20, yeah, minus 20. So as I add heat, what happens to the ice? Yeah, this is degrees Celsius, right? Degrees Celsius.
Oh, yeah.
So it will melt, I'm sorry, it will heat. It will be ice at minus 19, ice at minus 18, ice at minus 10, all the way to 0. Right? Something like that. This is not up to scale, or not to scale. So it goes like this. You're adding heat, and the temperature rises. All right, great. Yeah. You're adding heat, the temperature rises. And then when it reaches 0, you add heat, but the temperature actually does not rise. You just change the phase. The ice melts and becomes liquid. So the temperature itself will not increase, but it changes its phase. So it remains, you're adding heat, and the temperature is not increasing. Once all the ice melts, becomes liquid, then the temperature will start to rise. Starts to rise until you get to 100, right? Again, yeah, this is minus 20, so it's, you know, not up to 100. Then you start getting what? Water at 100 degrees, and you're heating it. Starts to become vapor or gas or steam. Yeah. So the any heat you add will cause water to change to vapor or steam. Until all the water becomes steam at 100. And then any heat you add will cause the steam to be even hotter steam. So it starts to rise again. So here, the slope of this curve will be called the specific heat of ice. The slope of this curve is the specific heat of water. The slope of this curve will be the specific heat of the gas or steam. Yep. And then these horizontal lines will be the latent heat. Yeah, called the latent heat. So if you're in the same phase, let's see. So the specific heats, the relationship between Q and the specific heat, assuming again let's say you have liquid water and it's between 0 and 100 degrees. Okay, you haven't changed phase yet. So Q, the amount of heat needed to raise the temperature would be the amount of object that you have, the mass of the substance that you have. Do they use? Yeah, they use capital M. Capital M. This is the amount of substance that we have. Because if I add 1 joule of heat to 1 gram of water versus 1 joule of heat to a swimming pool or 10 grams, it doesn't have the same effect. It doesn't cause the same rise in temperature. So it has to have, it has to do with the amount of substance you have. And then C is the specific heat, and then the change in temperature. Now in here you have the freedom to use temperature in degrees Celsius or K. Why?
Because pressure doesn't matter.
Because it will change, so the difference will even it out.
Yeah, it's the change. Yeah, and remember what the difference between K and C are. You add 273, right? So if you add 273 to the initial and you add 273 to the final and then take the difference, the 273 cancels anyways. So when you have a difference in temperature, in that case it doesn't matter. But if you just have the temperature, be safe and use the K scale. Okay, so now there are tables that give you the specific heats. For example, specific heat of aluminum is about 900 joules per kilogram per Kelvin, right? The left side is what? What units here? Joules. Joules. It's heat. And so this is the change is in degrees Celsius or Kelvin. 1 degree Celsius, an increase of 1 degree Celsius is the same as an increase of 1 K, right? Yeah. So, and this is kilograms. And so if I want to get joules, right, this is kilograms, this is, let's say Kelvin, and this is a joule. If I want the left side to be a joule, I need a joule on top. I needed to cancel the kilogram and the K, right? And that way I would have the right units. So, for instance, copper, it's 385. Specific heat of ice is about 2090. Water is 4190. There are others, yeah.
So if like you're given specific heat in joules per kilogram Kelvin, you could just technically replace the Kelvin with the Celsius? I don't know if that's
Yes,
valid. Okay.
yes, yeah. This is per Kelvin or per Celsius. It's the same, yeah. Because the
There's
change,
difference.
yeah.
Will we ever see an example where the temperature is, if we have to use Kelvin?
In here,
Yeah.
whenever you're making it, taking the subtracting the two temperatures from each other, it does not matter.
So we'll, okay.
Yeah, it does not matter. Yeah. Well, I will stop. For the group who I will see you in about 10 minutes, please hang on. And,
Yeah, let's see what
or actually you can go
Because
to
we'll have to
the
know
PS 105 or what was it? Yeah, all right, I'll see you there.
I asked him to just